Welcome back everybody to the second part of this tutorial. In this part I will show you how to write your code in order to set up the clocks for the STM32 microcontroller. If you didn't see yet the first part, the introduction, please click on the right top corner. Hope you will enjoy it. Here we are in our second part of this tutorial, which we will see how to set up our clock for our microcontroller, the STM32F407. So let's first open the datasheet of this microcontroller, and let's go to the page 18 in the device overview here, and the block diagram of our microcontroller. So let's zoom in here and see what's in. So our tutorial aims to set up two clocks. The first one, the system core clocks for the ARM Cortex M4, which maximum frequency is 168 megahertz, and the second clock, the clock for the buses. The buses, as you can see here, the AHB APB2, APB1. So these buses are from the AMBA protocols from ARM. AMBA mean Advanced Microcontroller Bus Architecture. So as you can see here, we have the main system bus called the AHB, which maximum frequency is 168 megahertz. The AHB mean Advanced High Performance buses. And then the second kind of buses, the APB, as you can see here, APB2 and APB1. The APB mean Advanced Peripheral bus. So as you can see here, the APB2 maximum frequency is 84 megahertz, and the APB1, which maximum frequency is 42 megahertz. So here, as you can see here, APB2 drive these peripheral like SDO, the SD card, timer 1, timer 8, user 1, analog digital converter, and the APB, for example, drive the digital analog converter, the E2C3, timer 14, real-time clock, etc. So now in the screen appearing a diagram made by myself, so to understand more the architecture of the clock inside our microcontroller. So let's start from the right. From the right we have the three buses: the AHB Advanced High Performance bus, and the APB1, the APB2, the peripheral bus. All these three buses are derived from the system core clock. So the system core clock, which maximum frequency is 168 megahertz. So this clock, the system core clock is clocked by can be clocked by three different clock. The first one, as you can see, the external clock, which frequency vary from 4 to 26 megahertz. The second clock, it can be an internal RC clock, which frequency is 60 megahertz, and the third one is the PLL phased loop, which help us to reach the high frequency, which is 168. For example, if we choose source clock for our system core clock directly, the external clock, our maximum frequency will be 26 megahertz. And if we choose the internal clock, our frequency of the system core clock will be 60 megahertz. So it's too low compared to the maximum frequency, which is 168. So in order to reach this maximum frequency, we have to use the PLL. This PLL multiplied the frequency in order to reach the 168 megahertz. So here let's open our IDE. So here we have our empty project. If you don't know how to make empty project, please click in the right top corner. There's a link in video made by me explaining how to set up your first project. So here as you can see, here we have an empty project here. So before start coding, as you know, we have to add the appropriate driver firmware for our project. So here for setting up our project, we have to add two driver firmware, which are the RCC and the flash. So select this this folder or group and right click and select added file. Go to our driver here, open it, go to library STM32 F4 STP driver here, and source, and we're gonna looking for the RCC and flash. Here the flash and here the RCC, and as you can see here we added the flash and the RCC. So now let's go to the product directory and check if this header file are included, the flash header file and the RCC header file. So we go to the product directory. We can do like this, open the folder of our project directory and open this this configuration header file, and here we have to check if this header file. So let's put it here and let's put, so here the flash header file, where is it? We have to include it here. We have, here it is. We have to increment okay, we have to increment this, and the RCC are by default incremented, included. So we save and we close this header file. So here our project is ready to go. So before I want to explain something before starting coding our program. After the reset of the device of our microcontroller, the microcontroller were running with the internal, by default, with the internal RC 60 megahertz after the reset, and before executing our code inside the main, he will execute the startup STM32 F4. So let's open and check it. So inside this STM F4 we have the system init function. So the system, as you know, the system init function is located here in the system STM F4 file, source file here. So let's go here to the system init. So the system init function aims to set up our clock for our project. So in this tutorial I will not show you how to modify your how to modify this code in order to obtain your appropriate clock, but we will make this inside the main file. So in this part we will try to set up the clock in buses at their maximum frequency, which is 168 megahertz for the system core clock, and the AHB 42 megahertz for the APB1, and 84 megahertz for the APB2, using the external 8 megahertz crystal clock. In our case, for the STM F4 Discovery board, the external crystal clock is running at 8 megahertz. So so our main goal is to determine, as you can see, the divider in multiplication factor, the PLM, PLP, PLQ, AHB division factor, APB1 and APB2. So let's start here. The first thing though, we're gonna reset the clock to their uh, default states. So the first thing that we let's split the screen here, and let's open the RCC source file here, and we're gonna find the this function here, the RCC init, the reset the clock configuration to the default reset state. So we copy this and we paste it here. Now the second thing, we're gonna enable the external clock HSE, which means high-speed external clock. So enabling the external crystal clock. So here we're gonna need this function here, this function RCC, normally this one, AHC configuration here, and this function configure the external high-speed oscillator. So yes, we copy this and we paste it here, and this function have one parameter. This parameter can take 3 value on, off, bypass. So we're gonna copy this and we paste it right here. So as you can see here, the note after enabling the external clock, the application software should wait for the HSE ready flag to be set, indicating that the external clock is stable and can be used. So for this, we're gonna need a function here, RCC wait for the external clock startup, just here, and this function wait for the external clock to start up, and we copy this and we paste here. So this function wait for this flag to be set and return success if this flag is set, otherwise return error if the timeout is reached. And so here we have this function return a value, success or error. So type of error status. So we're going to create a new variable here, type of error status. So we're gonna error status, we're gonna call it error STS, for example, the error status here, and we copy this and we paste it here. So the value of the external clock, the value, it can take 2 value, success or error. Success mean the external clock is stable and ready to use, or the oscillator not ready yet, the timeout is reached. So there's error for the external clock. So depend on this value, we're gonna write our code. So we add a condition here. So depend on the error state value. So we copy this, if error state value equal to success, the first value here. So here external clock is okay, else mean external clock not ready to use, means clock configuration. So else mean there's error here, and for example, you can write a code. You can turn on LED to indicate that T is not running well. And for example, we can put here condition while 1. So if there's error, you can write your code here and turn on LED indicating that there's error here. So we're gonna continue writing our code here. If the error state equal to succeeds, mean the external clock is okay. So the first thing we're gonna move right now to the PLL to determine their parameter here. So we need this function here. We open here and we go the RCC, where is it? PLL configuration here. As you can see here, we have 1, 2, 3, 4, 5 parameter here. The RCC PLL configuration. So we copy this. I'm sorry, we copy this and we paste PLL config. And now we move on for the first parameter, which is here. The first parameter is that the RCC PLL source specifies the PLL entry for the clock source. It can be the HSI internal clock or the external clock. So of course we're gonna choose the external crystal clock here, and we're gonna copy this and we paste it right here. So here we have our external clock connected to the PLL. Then the PLM division factor, which division factor for the PLL VCO input clock. So this parameter must be a number between 0 and 63. You have to set the PLM correctly to ensure that the VCO input frequency range from 1 to 2 MHz. It's recommended to select the frequency of 2 MHz to limit the PLL jitter. So we're gonna select 2 MHz for the VCO input here. So as you know, the crystal for the discovery board is 8 MHz. So 8 divided by 4 equal 2 MHz. So we're gonna put here the division factor here equal to 4. So the VCO input is equal to 2 MHz. Now let's move on to the second multiplication factor, the PLN. And here the PLN specifies the multiplication factor for the PL VCO output clock. This parameter must be a number between 192 and 432. You have to set the PLN parameter correctly to ensure that the VCO output frequency is between 192 and 432. So the VCO input is equal to 2 MHz. So let's multiply this. Let's choose a number multiplication factor of 192. Why not? So we open the calculator here and we multiply the 2 MHz by 192. Gonna have 384 MHz as the VCO input. 384 MHz is inside the range. As you can see, the range is between 192 and 432. So it's correct. So we copy this value, for example, and we put it as PLN and we paste. So the VCO output is equal to 384. Now we move on to the PLLP here. Sorry. To the PLLP, specify the division factor for the main system clock. This parameter must be a number in the range 2, 4, 6, or 8. So now we have to determine our system clock frequency, which we want to set at their maximum frequency, which is 168 MHz, 168 MHz. So let's try to divide by 2. So for example, 384, if we divide it by 2, we're gonna have 192 MHz. 192 MHz is above the limit, which is 168 MHz. So system core clock can't run with 192 MHz. So the division factor for the PLP is not correct. So let's try 384 divided by 4. Divided by 4. So 96, so it's too low compared to 168 megahertz. So this is not gonna work. We can't determine our maximum frequency 168. So what we're gonna do right now, we're gonna erase all this parameter here, 192 for the PLP here, and we're gonna start from the right to the left, from our desired frequency, which is 168, to the left till reach our 8 megahertz crystal clock. So let's start here by 168. As you can see here, follow in the diagram, the PLP output of the division factor is 168. So 168, and with PLP equal to 2, so 168 multiplied by 2, yes, multiplied, we multiply instead of division because we are in reverse way. So 336. So 336 as VCO output is correct because it's inside the range 192 and 432. So if we choose, for example, the PLP equal to 4, equal 4 mean 168 multiplication by 4, we're gonna 168 by 4, we're gonna have 672. It's out of range, as you can see here. So the only PLP division factor is equal to 2. So we're gonna put 2 for the PLP here, and go forward here. So the VCO output right now is equal to 336 megahertz. So we're gonna determine right now the VCO input. As you can see here, the VCO input, the frequency is between 1 to 2 megahertz. So it's recommended 2 megahertz. So if we choose the VCO input 2 megahertz, the PLLN will be equal to 168, but 168 is out of range. As you can see here, the number of the PLLN should be between 192 and 432. So so it's not correct. So we go for 1 megahertz as VCO input. So if the VCO input equal to 1 megahertz, the PLN should be 336, and of course the last one, PLM, should be 8, and the last parameter here, we left the PLQ, specified division factor for the OTG-FS SDIO. This parameter must be a number between 4 and 50. If the USB OTG is used in your application, you have to set the PLQ parameter correctly to have 48 megahertz. The SDU energy need a frequency lower than or equal to 48 megahertz. So so we're gonna put this, if we put this PLQ division factor by 7, so the VCO output is equal to 336. 336 divided by 7 is equal to 48 megahertz, which the desired frequency. Yes, of course. So let's summarize here. Here we have our let's start from the crystal clock. Here we have 8 megahertz crystal clock multiplied by 8, divided by 8 by the PLM division factor is equal, we have 8 megahertz as VCO input. 1 megahertz multiplied by the PLN 336, we will have 336 megahertz as output, VCO output, and the 336 divided by 2 gonna get 168 megahertz, which is our desired frequency. So now we finish with the PL division and multiplication factor. Now we go to the PLL command. We're gonna enable the PLL here, so enable or disable the main PLL. So we're gonna select this and we copy here, and here we have two parameter can be enabled or disabled. So we're gonna enable this. So the note here: after enabling the main PLL, the application software should wait on PLL ready flag to be set, indicate that PLL clock is stable and can be used. So the same thing as the external clock. So we have to go for this function, get RCC get flag status, and here we're gonna copy this and we paste it. So check whether the specified RCC flag is set or not. So here we have our PLL flag. The main PLL clock is ready. This function indicates that this flag is set or not. So we copy this, reset. So this thing mean wait till the PLL flag is set. So we're gonna wait for the PLL until is ready. So now let's move on to the three division factor, the AHB APB1 and APB2. We're gonna determine this. So AHB APB1 and 2 configuration, and here we go to the both function here. Where is it? High speed clock configuration. So this function configure the AHB clock for the AHB clock. So we copy this and we paste here, and this parameter can be this parameter is defined the AHB clock divider. This clock is derived from the system core clock, which is right now 168. So the AHB, we want that the AHB is running at 168. So we're gonna choose the division factor equal to 1. So we copy this and we paste right here. So the same thing for the APP1, the APP2. So here we go to the P clock, peripheral clock 1, and we copy this. The peripheral clock 1, the APB1 should be maximum frequency should be 42, which means 168 divided by 4 equal to 42 megahertz. So we copy this and we paste here, and the same thing for the AHB2. Configure the high-speed APP clock here, and we copy this and we paste here, and the APB2 maximum frequency is 84 megahertz. So 168 megahertz divided by 2 equal to 84 megahertz. So we're going to choose the RCC HCL clock divide 2. Now I'm going to select the PLL as system core clock. As you can see in diagram here, so we go for the system clock configuration here. We configure the system core clock. So we copy this, here specify the clock source used as system core clock. It can be internal clock or directly the external clock or through the PLL. So we are using the PLL, so we're gonna choose the third parameter here, the system here, And before finishing, we have to set the flash latency here. Flash latency is inside the flash source file here. So here, let me explain you something. We open the second data sheet here, and we go to the page 9 here, and let's zoom in here. So here we have to know the wait state that need the flash memory. So here the number of flash memory wait state latency is defined according to the frequency of the CPU and by the supply voltage. So here our supply voltage of our board is between 3 and 3.3 voltage. So we are inside this column, and our height clock speed is equal to 168 megahertz. So we are here right now, and the wait state is equal to 5 wait state here. So we go here, we come back to the flash driver firmware here, and we go to the flash state latency here, and we copy this. As you can see here, set the code latency value. It can be from 0 to 7, and we put it before enabling the clock source here. Let's put it here. Set the flash latency, and we paste this, and as we saw before, we need 5 wait state. So we're gonna select flash latency 5, and we paste here. So let's compile our project and see if we have an error here. Let's download it, and 0 error and 0 warning. So that's all for this tutorial. If you found this tutorial interesting and helpful, please push the like button and subscribe to this channel. And if you want to help this channel, there's a link in the video description below. And if you want to see the next and final part, the third part, please click in the right top corner.